Question number 31. A cannonball with a mass of 10 kilograms is fired from a cannon horizontally at the exact same time the cannonball is dropped onto the ground below, assuming air resistance is negligible, which hits the ground first. So we have a cannonball that's fired out here, and of course it follows a parabolic path of a projectile, and then one of them goes straight down. So one is going like a projectile and one is going straight down. Which hits the ground first? The most important thing to remember is that the amount of time that it takes for any object to fall is equal to the square root of 2 dy over g. So the only two things that really matter are the height, which is dy, and g. Now obviously one of them has a very high dx value, because it's fired from the cannon, so it's very high, and the other one has, since it's just dropped, its dx value is 0. But dx has nothing to do with the amount of time it takes to hit the ground. So the answer to this question is they both hit the ground at the same time. 32. Two students use a boat to cross a river that is flowing at 4 meters per second, and the boat is traveling 5 meters per second straight across the river. What is the resulting speed of the boat relative to the shore? So the first thing that we're going to do is draw the vectors. What we have is a boat that is moving in this direction, straight across the river. Let's draw a river in here. It's going straight across the river, and the vectors are show that it is traveling at 5 meters per second, and the river itself is going in this direction at 4 meters per second. So which direction is the boat actually going? Well, it's the resultant of those two vectors. So we can do that with the Pythagorean theorem. C squared is equal to a squared plus b squared, which means that the resultant, the square of the resultant, is equal to 4 squared plus 5 squared, which means that it's equal to 16 plus 25. So c squared is equal to about, let's see, 41. So c is equal to the square root of all of that, 41. So it's equal to about 6.4 meters per second. When you're looking at a question like this, you need to look at the magnitude of these velocities and realize that the magnitude of the resultant, when we have a right triangle here, the magnitude of the resultant is always going to be greater than either one of these. So one of these is 4, one of these is 5. The resultant is going to be greater than 5 no matter what. It has to be, as long as this is a right triangle. The data table at left shows time, position, and velocity data for an object thrown vertically upwards. Based on these data, at what time will the object reach 0 velocity? So really all we have to do is continue our graph here, or our table, time versus velocity. And we can look at this and say at 0.6 it will be 4, at 0.7, 0.8, 0.9, and so on. It will be 4, 3, 2, 1. So at 1.0 seconds, it should be 0. So just continue this table the same way that you would based on predicting this data. You can see the velocity is going down 10, 9, 8, 7, 6, 5. The position is going up. Time is going up as well. A box slides across a rough floor with an initial velocity of 5 meters per second to the right. So the velocity is going in this direction. Friction is acting on the box as shown. So what's happening to the velocity of the box? Well, if the velocity is this way, this is the velocity vector, and friction is this way, it's opposing the velocity, that's the force of friction, then the box must be slowing down. whenever the force is acting in the opposite direction to the velocity, we have slowing down. If it were acting in the same direction, we would have speeding up, although friction is not going to act in the same direction as the velocity in a case like this. A freely falling ball has a constant acceleration of 10 meters per second squared. That would be g. That's 9.8 rounded up to 10. What can be said about the velocity of the ball? Well, it means that the change of velocity is 10 meters per second every second. That's an R. Every second. So we could say that if the ball is falling, that the velocity is increasing by 10 meters per second each and every second. A ball is thrown straight up into the air. At its highest point, what is the ball's velocity? Well, when a ball goes up and then comes back down, at its highest point, its velocity is equal to 0. Because it starts off with a positive velocity going up, it ends up with a negative velocity on its way down, but at the top, guess what? It's not moving. What is the acceleration at that point? Well, the acceleration never changes. The acceleration is gravity, which is 9.8 meters per second squared, or 10 meters per second squared if you round it. Acceleration is constant. It never changes. Number 37. A car begins with a velocity of 30 kilometers per hour. After 1 second, the car's speed is 32. After 2 seconds, it's 34. After 3 seconds, it has a speed of 36. What is the acceleration of the car? All we really need to do is look at our formula for acceleration. Acceleration is equal to change in velocity divided by change in time. So let's pick any of these two points. So the first point after 1 second is the simplest, and so the change in velocity is 32 minus its initial velocity, which is 30, which means its change in velocity is 2 kilometers per hour, and divide that by the amount of time, which is 1 second. So 1 second, we end up with 2 kilometers per hour per second, and that is speeding up. Questions 38 through 40. An object is at the end of a string and it swung around in a horizontal circle as shown at left. You can see that in this case it's going in a clockwise direction, so because the arrow is pointing like this, so going around. Draw the vector for velocity at the point where the object is. So the vector for velocity is tangent to the circle. It's right there. The vector for the acceleration of the object, well, acceleration and force are always pointed in towards the center and at right angles to that tangent point on the circle. The centripetal force acting on the object is also in the same direction. So we have the tangential velocity is in this direction, and both the centripetal force and the centripetal acceleration are both acting towards the center of the circle. Question 41. The force between the two objects is equal to F. What is the force between the other three pairs of objects? So looking at this first one, treat this like a ratio. Remember that force is proportional to m1 times m2 over the distance between them squared. So looking at the first two objects, we'll just treat them as our basis here, 1 over 1 squared. So now let's look at how these others change. So for this second set, we have The mass of the first ball is unchanged. For the second one, it's twice as big, and the radius, or pardon me, the distance between them squared is the same, so that's equal to 2 over 1. So when we change the mass, we double it. We double the force. So it's equal to 2F. Looking at this one right here, the two masses are unchanged, so we have 1 times 1 divided by 2 times the distance between them squared, so we end up with 1 over 4. So in this case, the force is equal to 1/4 of the original force. The last one over here, we have this mass right here is twice as much, so we have 2 times the mass times the other mass is 2, and the distance is also 2, and that's squared. So we end up with 4 over 4, which is equal to 1. So for this set, the gravity is equal to the original one. It's 1 times the force. All of this is done with ratios. Remember, the first mass times the second mass divided by the distance between them squared. If we just put in how many times these change, then we can calculate a ratio, and we can get the ratio of the new force to the old force. Calculate the kinetic energy of a 4 kilogram bowling ball sliding across the floor at 6 meters per second. Kinetic energy is equal to 1/2 mv squared. So we substitute, we get 1/2 times 4 kilograms. I'll put that in parentheses. And 6 meters per second, and this is squared. This is not 6 meters per second squared like acceleration, where the units are squared, but the value here of 6 is what's being squared, as well as the units. When we total this up, we have 1/2 times 4 times 36, and we end up with 64, and our units end up being kilogram meters per second squared, and that is otherwise known as a joule. So our final answer is 64 joules. What happens when work is done on an object? Well, we haven't spent a lot of time talking about this, but work is equal to force times distance, and our units for force are joules. We've also talked about potential energy and kinetic energy, and the units in those cases are also joules. If the work that we do against gravity is equal to mgh, and potential energy is also equal to mgh, we can see that when we do work against gravity, we increase potential energy. Likewise, if we do work on an object where we cause it to speed up, we change its kinetic energy. And in other cases that we'll learn about later, when we do work and cause friction or cause heat, we're also transferring energy. So in all of these cases, when we do work on an object, we are changing the energy of the object. So energy is transferred, if I can write on this iPad. So the big concept here is that energy is being transferred whenever we are doing work. It's going from one place to another. Number 44, Nan pushes an 8 kilogram box with horizontal force of 9 newtons for a displacement of 10 meters across a rough horizontal floor. Lauren then lifts the same box and places it on a shelf 2 meters high. What is the total amount of work done by both girls? Okay, so we've got two separate types of work being done. The first is the work that's being done by pushing the box across the floor, and that work can be calculated as a force times a distance. So we have a force equal to 9 newtons times 10 meters. That's 90 newton meters, otherwise known as 90 joules of work. Next, we're doing some work against gravity. So that work is also a force times a distance. The force is the force of weight, mg, and the distance is height. So the work done against gravity is equal to mgh. We know that m is 8 kilograms. G will just use 10 meters per second squared. And h is a shelf 2 meters in height. We multiply those all together. We get 8 times 10 is 80 kilogram meters per second squared, otherwise known as a newton, times 2 is 160, and 160 newton meters is 160 joules. If we add those all together, we get 250 joules of work done total. It's, again, important to note that when we push the box along the floor, we've done 90 joules of work, and then when we lift the box up, we do 160 joules of work. If we had just lifted the box up first and then carried it, then we would have done only 160 joules of work, because carrying the box does not do any work, because we're not acting against a force, and so we only have the work done against gravity, lifting the box. But when we slide it across the rough floor, we're doing work. A falling stone weighing 15 newtons encounters 9 newtons of air resistance. What is the net force acting on the stone? So let's go on and draw this like a free body diagram. We've got 15 newtons down, and then we have 9 newtons up. So we have to subtract these two. So the net force is equal to 15 newtons minus 9 newtons. And we'll keep track of our directions here. The result of this is 6 newtons, and the magnitude of the down is greater than the up, so the result is in the down direction. So you have to just subtract the two since they're in opposite directions. Number 46, a force of 30 newtons gives a mass and acceleration of 5 meters per second squared. What force will give the same mass and acceleration of 15 meters per second squared? Well, force is equal to mass times acceleration. So we could just as easily say that acceleration is proportional to the force applied when the mass is the same. So if we want 3 times the acceleration, we're going to need 3 times the force. It really is just that simple. If you want to do it the long way, which is quite all right with me if you're given all the proper information, you could calculate the mass first. This is the long way, but mass is equal to force divided by acceleration, which means it's equal to 30 newtons divided by 5 meters per second squared, which means the mass must be 6 kilograms. You could then calculate the force required to accelerate 6 kilograms of mass by 15 meters per second squared, and you would end up with a force of 6 times 15, which is 90 newtons. Notice that back over here, when I said that we needed 3 times the force in order to get 3 times the acceleration, 3 times the force, 3 times 30 newtons is equal to 90 newtons. So either one is going to give us the same answer. This way is not terribly difficult, but this way is a lot easier, just by doing it as a ratio or proportionality, because again, the acceleration is proportional to the force if the mass doesn't change. An unfortunate bug splatters against the windshield of a moving car. Compare the force of the bug on the car to the force of the car on the bug using one of Newton's laws. Well, let's see. Newton's first law is inertia. So what does inertia have to do with the bug and the car? Well, both of them have it, but not really appropriate. 2 is Newton's law. The acceleration is equal to the force divided by the mass, or generally the way we write it, force equals mass times acceleration. Again, not terribly instructive, because we're looking at each force, and we don't know things like mass and acceleration. The best one is Newton's third law. Newton's third law says that for every force, there's an equal and opposite force. So, and that's generally action and reaction is what it's called, although that implies that one follows the other. The truth is, they happen at the same time. For every force in a pair of objects, and there must be a pair of objects, the force on one is equal to the force on the other, but in the opposite direction. So the force of the bug on the windshield is the same as the force of the windshield on the bug. So those two forces are exactly the same. It's the same thing that happens when you're standing on the earth. Forces are the same. When you're standing on the earth, this is me standing on the earth, there's a force of gravity pulling down on me, but remember that there's also a force of me pulling up on the earth, and those forces are the same. If there is no net force acting on an object, what must be true about the object's motion? Well, one of the most common things that people think about is if there is no net force, people tend to think that that means it's not moving. Well, that is not always true. If there is no net force, that means that velocity is not changing. If velocity is not changing, that's the same thing as saying constant velocity. So that's the correct answer. Is it possible that the object is not moving? Well, sure, it's possible. But what if the object is coasting? It can be coasting along like a hockey puck on ice or an object floating through space. All that no net force means, according to Newton's second law, or Newton's first law rather, of inertia, is that an object in motion remains in motion and an object at rest remains at rest unless there's a net force that's not zero. So if the net force is equal to zero, what it means is that the object's velocity is constant, whatever that velocity happens to be. Number 49, the weight of an astronaut standing on Mars is 200 newtons. What is the gravitational force between the astronaut and Mars? So we have Mars right here, and we have the astronaut right here. And he's standing on Mars. Maybe his feet aren't quite touching in my drawing right here. He's standing on Mars. So there's a net force acting on him. Well, that force is actually acting on him and acting on Mars. And the reason is that gravity is equal to that big G times the mass of the astronaut times the mass of Mars divided by the radius of Mars squared, whatever that happens to be. But the force is the product of the astronaut and Mars. And that doesn't matter whether we're talking about the force down or the force up. The force is exactly the same, so just in opposite directions. So the force is 200 newtons. It's the same. Last question. Compare and contrast mass and weight. All right, so let's take a look. Mass. Weight. So mass is basically the same thing as inertia. All objects that have mass have inertia, and we measure inertia and we also measure mass with the units of kilograms. Weight is just a force. What force? Well, it's the force of gravity. Okay, but it's just a force. The units for weight are newtons, not kilograms. How about dependencies? What does mass depend on? Well, mass does not depend on gravity. Which means if I'm on the moon, or I'm on Mars, or I'm floating in deep space, my mass is still the same. But my weight, on the other hand, does depend on gravity. Which means that if I move to the top of Mount Everest, my weight might get a little bit lower because I'm a little further away from the Earth. If I go to Mars, my gravity is a little bit lower, my weight is a little lower. If I'm on the moon, my weight is a little lower. So the important thing is that weight depends on gravity and mass does not depend on gravity. Again, you need to know the units. We measure weight in newtons and we measure mass in kilograms. You guys very often mix those two up, but you need to make sure you know the difference. Good luck on your final exam. I hope this has been of help to you.